Hey Debbie, can you see and hear us okay?
Yes, we can.
Thank you so much.
You're welcome.
They can now.
They can now.
I don't know where that's coming from. Here?
Hello.
That's better. Okay. So the first thing tonight is...
Are you going to use the wireless?
No, I'm not going to walk for it.
Okay.
Is test 1 for Thursday the 21st. So that's next Thursday. And what I'm thinking is chapters 1 through 6. I don't know if we'll get all the way through 6 or not. Wherever we get to next Tuesday is where we'll stop. And the way the test is going to work is it'll be 40 questions, multiple choice, A, B, C, or D, and I'm not one of these all the above or none of the above. The answer will actually be sitting there looking at you. All right? You need to make sure that you bring your calculator. I'll remind you again next Tuesday on this. You know, the tables and formulas that you use, especially table A, and then those first couple pages of those tables and formulas that you printed out of D2L, I mean, they got all the formulas we've been using, right? And it tells you how to do whatever. You should also bring an ID, because obviously Rob knows you folks here. I know them folks in Kingsport, but there's going to be other people going places, so that's the deal. Also on Tuesday, like I don't really hand out what I would call a study guide, but I hand out my thoughts. In other words, out of each little piece, you know, what I think we should be able to do and everything like that. So I'll do that on Tuesday after we see how far we went. Okay. You folks that are streaming, I sent you an email today and asked you, I gave you some options about taking the test, and I definitely need an answer. All right. So, you know, as soon as you can do that, I would appreciate that. You folks will be here. You folks in Kingsport, you'll be where you're at. It's everybody else that I got to worry. The last thing we were doing on Tuesday was we were talking about least squares regression line, right? And I give you and what I thought I should do before I start giving you any facts, I want to remind you a little bit of something. And remember, anytime that we see a regression line in this class, the one we always work with is the least squares. And remember, it had this form. Remember, I read that as y hat because I want you to know, you know, there's actually y values in the data, and so this is something that's being predicted from the line. And remember that the b is your slope, and the a is your, that's your y-intercept. So what I would like to do is I'd like to go back and get another one of these and show you how I interpret the slope, show you if I can interpret the y-intercept, I will, and then show you how to make a prediction, right? How do I use this line to make a prediction? And so what I was thinking is I'd come to like a homework problem, if you don't mind, and the problem I wanted to look at was on page, it's on the bottom of page 156. And then it's on the top of 157. And the problem here is 5.39. Because it pretty much has, you know, everything we've talked about in this problem. And it says this: one of nature's patterns connects the percent of adult birds in a colony that return from the previous year and the number of new birds that join colonies. Here are the data on 13 colonies of sparrowhawks. So your individuals here is you have 13 colonies. Yeah, they're sparrowhawks. And we got a nice little table. We have two variables measured on them. One of them is the percent of adults that return to next year. And our other quantitative variable is the number of new adults that join the colony. Okay? So two quantitative variables. And in the textbook, it don't really say which one should be the explanatory and which one is the response, but in the little table, it tells me that's my x and that's my y. So remember, this is the explanatory, because the explanatory always goes on the x, and this is my response. The response always goes on the y. So they're kind of thinking that maybe the percent returning to the colony the next year will have some kind of influence or help explain the number of new adults that join. And so the problem says, you saw in exercise 429 that you had a correlation. I'm going to write it down for you. The correlation was a negative 0.748. Now, I got a question for you. What does that mean? It means we're seeing a negative association, right? We're seeing upper left to lower right in a scatter plot when we make it. We're also seeing that that's where my moderately strong is. And so to interpret that, it's telling me that I'm seeing a moderately strong negative linear relationship or association. And I want to underline something for you here. You know, I'm giving you the strength, I'm giving you the direction, and I'm giving you the form, right? Those are the three things we're supposed to tell everybody, and I'm getting all that off the correlation. Now, what I would like to do is it says, find the least squares regression line for predicting y from x, make a scatter plot, and draw your line on the plot. Well, we're not going to do any of that by hand, so I'd like to come over here. I'd like to find chapter 5. That wasn't my normal routine because I don't have it sitting on the desktop here, so I got them on my Q drive. So this is 539. And look, all that really is, that's just a lazy man's way of putting that table that's in the book into Minitab. Notice the first column is the percent returning, the second column is the number of new birds. And I would like to give you all this at one time. I want the scatter plot, I want the regression line on there, and I would like to actually have the equation. And I think I showed you that last Tuesday, but we would go to stat, regression, right? That's where we go. And remember, I always talk about fitting the line to the data. That's the way I think about it. The reason I'm telling you that is because that helps me remember, I want to go to fitted line plot, okay? And then it wants to know what the y is. And remember, back here, the y was the number of new birds. And then I made a big deal about it not calling it the explanatory variable, but calling it the predictor because, hell, that's the reason we want the line is we want to make a prediction. And so that's the percent return, and I click OK. Everything I ever wanted to know about that data set is looking at it. The line's there, the scatter plot's there. Hell, the line's actually drawn on there, correct? Now, you see this guy right here. There's your least squares regression line, right? That's that y hat is equal to a plus bx. Now, I'm going to come over here, and if I can remember, in this problem, 539, and this is part A, so I would write it like this. Now, Minitab doesn't do it, but, I'm going to put a little hat on that so you know this is something the line is predicting for us, and it's equal to, 31.93 minus 0.304% that return. Now, notice this looks like a y hat to me, and there sits my x. And I warned you about this on Tuesday. Our variables always have a meaning, so a lot of times they put words in there. Okay? Now, we've done everything Part A says. Now, what about Part B? And Part B says, explain in words what the slope of the regression line tells us. In other words, what they're asking me to do is to interpret the slope. Now, here's the thing. Anytime anybody gives you any of these problems, we can always interpret the slope. Right? There's nothing, we don't have to worry about anything. We can always interpret the slope, and we always take the sign, and what I mean is, you see there's a minus sign sitting out in front of the slope, so immediately I know that my slope, which is my b here, is right? So I take the sign, because normally in the formula it's a plus. If it's a minus, you take it with it. It's telling me the slope's negative, and then I got a dumb question for us. Right? When I look here, and I see that red line, right? Because that's the equation of the line, that the one I have circled in red. Does that line have a negative slope to it? Does everybody remember that if we're this way, we're negative, and we're that way, we're positive, right? So it kind of makes sense. If you're going to see a negative association in the data, don't you imagine the line should have a negative slope and be sloped that same direction? That seems like an obvious thought there, right? Okay. Now, remember, when we interpret, we always think about increasing your explanatory variable by one unit, right? So here, for each additional Now, what's my explanatory variable? It's the percent returning, right? So for each additional percent of returning birds, the number of new birds that join the colony, because that's the way we're thinking about that, now remember, your response variable is either going to increase by the slope or it's going to decrease by the slope, and your slope is actually negative, so that's where the word you're going to decrease is by. What was it? 0.304. So for each additional percent of returning birds, the number of new birds that join the colony decreases by 0.304, and I always like to put this little part here because, you know, we're thinking about everything on the average here. That's not going to make you be wrong or right. Just throw that in there so you say, okay, on the average, this is what happens. Is everybody okay? So let me ask you this. Suppose we increase the percent to 2. What can we say about the number of new birds that's going to decrease? See, for 1, it's 0.304 you decrease by. If it's 2, he's calculating in his head, and I'm going to tell you, I think it's going to decrease by 0.608, right? So for 1, it's 0.304. For 2, it's 0.608. For 10, it's 3.04, right? So I'm multiplying. It goes like that, right? In other words, we think about what happens with 1, but hell, I can tell you what happens with 2, 3, 4, whatever. My big thought is, and what I want to get really, I don't know how else to say it to you. If the slope is negative, you're thinking about decreasing, because we always think about increasing or adding 1 to your explanatory variable. All right? And so I go back to the problem that's in the book. You know, and I told you, we can always interpret the slope. You give me some 2 quantitative variables, a scatter plot, the least squares regression line, whatever the slope is, I can interpret it, and I'll do the exact same thing to you every time. Now, I would have thought part C, that's part B. Right? You would think that we're interpreting, so why? Well, so here's what part C says in your book. It says, an ecologist uses the line based on 13 colonies to predict how many new birds will join another colony to which 60% of the adult from the previous year return. What's the prediction? In other words, what's the line tell you the number of new birds should be if you actually had a colony where 60% of the adults returned from the previous year? I would have thought C would have been, why don't we interpret the y-intercept? And that seems like a reasonable thing, right? Because I did that to you on one of them. But you understand why they're not. And I mentioned this to you on Tuesday, and I want to mention it again. If I sit here and I look, it looks to me like I'm from a little bit less than 40 to a little bit bigger than 80 for values of my explanatory variable, right? In other words, I've got colonies where it looks like maybe, 38% return up to maybe 81 or 82% returning. Do you see anything where I've got something close to 0 returning? No. See, we never go outside of that range of those values. Well, let me ask you this. How stupid is this? Suppose we were going to interpret the y-intercept and say, okay, let's say we have a colony and 0% of the birds returned from last year. So I'm looking at you all. When 0% returns, do I have a colony? In other words, interpreting the y-intercept here makes no sense. Didn't we do the same thing on Tuesday where I had one where it didn't make any sense? I can't be outside that range. And hell, it didn't even make any sense to let the explanatory variable be 0. That's the reason they go right to, can we make a prediction? Now, here's the way I think about it. Anytime somebody's going to ask you to make a prediction, they're going to give it to you in words, right? And they say, okay, an ecologist uses the line based on the 13 colonies to predict how many new birds will join another colony to which 60% of the adults from the previous year return. So in other words, they're telling me that the percent returning, and you don't know how hard it is for me as a math guy to write, not just to write, I'm trying to tell you that x is equal to 60, right? Now, I don't have to move the decimal place or anything because all my data is in actually percentages here. And so what do? If I want the number of new birds that my line is going to predict, I'm going to take that 31.93 minus your 0.304 times 60. And so somebody got a calculator will calculate this out for me. For some reason, I'm thinking it's 12 something or 13 something. Obviously, it's not a whole number because of the way we're working here, but I can't really remember what the number is. So 13.6. Now, students sometimes look at me and say, well, dude, you can't have 13.69. Well, the line predicted exactly, right? So somewhere between 13 and 14, 13 or 14 birds is what was predicted here. Now, that's exact. That wasn't reading up and reading across. And why am I saying that? Because if I come back here, and you remember the other day, I was doing this, right? I would have found my 60%. I'd have read up. I'd have read across. The line's telling me what I would read is 13.69, and that's exact, right? And so that's, anytime somebody wants to make a prediction here, they're going to give you the line, and you're going to plug in. Is there anything special about 60%? Could we have done 50? Could we have done 70, 75? You understand why I looked over here? Do you want to do 20? Do you want to do 90? I'm outside of the 40 to 80 again, right? I don't want to do that, okay? So that's how these problems work. And to me, that's like a typical problem up until the material we have now about, okay, can you interpret the slope? Can you tell me what you're seeing? I'm seeing a negative association, and everything here is matching up, right? Okay. So with all that done, I don't think I need that one now. When I come back here, I'd like to go back and so there's like a little more to add to this. And my first thought is I'm going to add some facts here. And I'm going to be honest with you, one of these is more important than the other three. And the first one is this least squares regression line, and these are facts for the least squares regression line, it makes a distinction between explanatory and response. In other words, if you start changing, you flip-flop them, you're going to get a different answer. Obviously. So here's the way I'm going to show you this. I just showed you the one where the percent returning was the X and the number of new birds was the Y. What about if I flip-flop them? All right? So what about if I come back here and I say, okay, let's go to a stat, regression, fitted line plot, and let's flip-flop these two. Now I'm going to give you this. The scatter plot's going to look similar, right? You're still going to see this negative association, but you're going to have a completely different line because you've interchanged all the X's and the Y's, right? So if I click OK, Actually, it's kind of crazy for me to do that because I don't even know how to make sense of telling you the lines look different. Well, the equations are definitely different, right? Because now you're predicting the percent returning from the number of new birds, and that's definitely a different line, right? I know everything looks the same. It's a different line. So it makes a difference which one you call the X and which one you call the Y, all right? Now, 2. And 2 goes like this, okay? If I look at this slope, that was the equation I gave you on Tuesday for the slope of the least squares regression line, right? Remember, B was the correlation times the standard deviation in the Y's over the standard deviation in the X's. Now, my first thought about this is, if R is positive, the slope is positive. I'm going to remind you of something about the standard deviation. The standard deviation is always bigger than or equal to 0. Correct? You can't ever have a negative standard deviation, and the only way you get the standard deviation to be 0 is if in your data set all the values are exactly the same, right? In other words, if I had 5 test scores and I wanted the standard deviation to be 0, they all got to be 90, 90, 90, 90, 90, right? Or they all have to have the same value. In other words, there's no spread. So if they're both positive, the way this slope gets its sign is from the correlation. In other words, if the correlation is positive, you're going to see a positive association. You're going to see a line on there with a positive slope. If the correlation is negative, then the slope is going to be negative. That's the one I just showed you with percent returning and the number of new birds, right? The correlation was negative. The slope of the regression line was negative. That's my first thought about the slope. The second thought is, and I'm going to leave that piece right at the top, a change in one standard deviation in X. In other words, you think about changing the X by one standard deviation. Whatever in the world your standard deviation of the X's is, one standard deviation corresponds to a change of R standard deviations in Y. So it's a weird thing. You would think it would be like a 1 for 1, right? If you changed your X by one standard deviation, you would think you'd change the Y by one standard deviation. But the way the formula is, because it's this R times that, so in other words, if you change what's in the denominator by 1, what you're really changing the numerator by is R times that. In other words, what happens is, you remember the value of the correlation is always between -1 and 1, right? The only time it's actually a 1 for 1 change is when R is equal to plus or minus 1. In other words, things are perfect. If R is anything other than plus or minus 1, a change in one standard deviation in the X corresponds to less than 1 in the Y. Kind of an interesting little thought there about the way that's all set up. Now, you might move 1 here, but you don't move a full 1 here on the Y's. It's less than 1 unless you're perfect. 3. 3 is like just a nice little thought to have. Somewhere on your scatter plot, there's the point, the mean of the X's and the mean of the Y's, and it turns out is on the line. Another way to say it is that least squares regression line passes through whatever that point is in your scatter plot. And it's somewhere on the scatter plot. Obviously, it's not going to be one of the data points, right? But there's somewhere I could put the X bar and Y bar and make a mark. The line will pass through that. Now, how does that serve me and you? Well, if we were doing stuff by hand, it would. Because that would be one of the 2 points I'd need to put it on there, right? But since we're doing Minitab, okay, so it's a nice little fact. The most important out of all these is the fourth one. Okay? Now, I'm going to kind of quote the book, and then I'm going to give you my hillbilly language, if you don't mind. Okay? And so we think about the square of the correlation. In other words, we're going to take the correlation and we're going to square it. Now, everybody knows that means you're going to multiply it by itself. All right? Okay? This tells me something about what we're looking at. And what it tells me is the fraction. This is where it sounds very much like the book of, so it's a fraction of the variation in the values of y that is explained by the linear relationship or association. Now, I got to be honest, before I do anything with this, the way the R squared always comes to us is you understand that if I'm going to take the correlation and I'm going to square it, then this is always true. Right? You know, even if it's negative when I square it, I make it positive, right? So R squared is always this fraction, right? This number between 0 and 1. The only way you get 0 if the correlation was 0. The only way you get 1 is if the correlation was minus 1 or plus 1. Any other time, it's a number between them, correct? The way it gets reported to everybody, nobody's going to tell you that the R squared is 0.526. They're going to report it to you like this. So I'm going to do it as a percentage. So in other words, it's not just the fraction of the variation, it's the percentage of the variation up at the top. And if that's the case, this is always true. R squared as a percentage is always a number between 0% and 100%. Everybody okay with that? That's the way it gets reported, right? We talk about it in terms of R squared, but we move the decimal place and we turn it into a percentage, right? So here, we talk about the percentage. Right? Sorry. We should have put that above that. Now, what does all this really mean to me and you? Well, I need to give you a little talk about how in the hell is this telling me anything about anything. So what I want to do is I want to come back here, and I'm going to stick with these these birds and all this, if you don't mind. Obviously, I'm going to turn things around and say the way I had it the first time. Okay? Now, there's something on this graph here that I didn't mention last week and I didn't mention earlier. Everybody see the box that's on the right-hand side? The little box up here on the right? That's the one I'm talking about. So it's telling me if I take my correlation and square it here and move the decimal place, my little R squared here is 56%. Okay? And so to interpret that, to say that in terms of what I just said, since with those guys that R squared as a percentage was equal to 56%. Okay? What does that mean? That means 56% of the variation in the number of new birds that join the colony is explained by linear relationship. It's explained by the fact that we think we're looking at a linear form, right? So all I did was I got Minitab to calculate it for me, and then I stuck it into that line I had before, right? So my percentage here was 56%. So it's 56% of the variation in the number of new birds that join the colony is explained by the fact that you have a linear relationship. Now, how's this doing this? Look. I'm going to give you this little thought, and I'm going to look at you for a second and see, did that even like just circle your head or did it just go on by? All right? So I know I see a linear relationship. How do I know that? I got the freaking line drawn on there, right? So I think I see something that's linear. I put the line on it, yeah? Now you understand, if I think I see a linear relationship and I see this negative association, well, the points are following that linear form, right? The points are actually following the line. Everybody understand that, yes? In other words, as I start changing, that ain't the right one. It's okay, my percentage won't change. I apologize. Are you shocked that 56% didn't change? Does the correlation care which one's called the explanatory and which one's called the response? What changes is the equation of my line, right? Okay. So look, as I start changing here, and just for the sake of things, let's say, I start increasing your percent return, right? Well, we know that the number of new birds is going to decrease because we're seeing a negative association, right? But they have to follow that form you think you're seeing. In other words, they're moving along this line, right? The points are. So is that forcing the Y value to change? Let me ask it to you this way. When I look here, and I look and I got my X and I got my Y, right? Do the Y values show you variability? Do the Y values have a positive standard deviation? Does the number of new birds, does it change as I go from one colony to the next? In other words, is there variation there? And the answer is, yeah. Well, the variation comes in two parts. One part comes from the linear relationship. R squared is telling you about that, right? In other words, 56% of the variation is coming from the fact that it's linear. That's forcing the value of Y to change as I go from one colony to the next because the percent return changes from one colony to the next. Yes? That's what R squared is measuring, is how much of it's coming from the linear relationship. Do you understand there's another part of variation? And the other part is, the scatter of the points about the line. R squared doesn't tell you anything about that. That's like leftover variation. So if 56% of the variation comes from the linear relationship, 44% of the variation comes from the scatter of the points around the line. How did I come up with 44? There's two parts, right? There's the part that comes from linear. There's the part that comes from the scatter of the points. If 56% comes from linear, 44%, whatever's left over, has to come from the scatter of the points about the line. Fair enough? Okay. Now, I got another dumb question, and I'm just full of them all the time now. Let's say I gave you this. And I said, okay, I know that R squared is 56%. Can you tell me the value of the correlation? She's shaking her head. So here's my question is, if R squared with a percentage is 56%, that means that R squared is that true? So if I've got something squared, does anybody know anything about this? I need to take the square root of it, right? So when I take the square root, I'm going to need help here. What's the square root of 0.56? I'm hoping it's 0.74 or something. Yeah. And so it's actually I know we're not math people, but I don't know how much you remember about when you take the square root of something squared. You actually get back plus or minus, right? And so which one is it here? The only way you're going to know the scatter plot showing you a negative association, a negative slope. That's how I know it's negative 0.478. All right? Now, remember, when I started this problem back here, right, all the way back here today, remember that problem gave it to me. But if they didn't give it to me and they just gave me the percentage, can you figure it out? You need a calculator, you need to take the square root, and then you need to have a scatter plot so that you can see is it a negative association or a positive one, because you're going to get both. All right? I just wanted to throw that one out there to you too. Now, can I put it in my hillbilly language? What's R squared really telling me? I think about R squared as a percentage, or just R squared, and you got the decimal, as in other words, what it's really measuring for us is, yeah, I know it measures that percentage of the variation and all that crap in terms of the linear relationship. But what it's telling me is how successful we were at fitting the line to the data. Think about it like this. Remember, I already showed you this. The closer I am to 100%, the better we did. Translation, the closer this is to 100%, the better the line fits the data. The further away it is from 100%, the line doesn't fit the data. So why do I care about this? Why do I care that somebody's going to, that this measures this? So let me ask you this. Suppose we're making predictions, and my R squared is like 10%. How do you feel about my predictions? At 10%, does the line fit the data very well? And the answer is no. And she's frowning at me, and she wants to tell me, look, if R squared is 10%, your predictions are worth crap, dude. You might as well just wad them up and throw them in the paper. But what about if my R squared is 90%? How do you feel about my predictions? They should be quite accurate, right? Because the 90% is telling me, hell, the line fit the data really well. So the closer I am to 100%, the better I feel about making predictions. Why? The closer I am to 100%, the better the line fit the data. That's the way I use it. That's the reason I think about the success rate, how successful we were at fitting the line. And back here, we're at 56%. So we're a little bit over half of the variation is explained by the linear relationship. How do you feel about making predictions? Well, I don't feel too bad. I'd feel better if it was 95%. I don't feel bad. I'd feel better than if it was 25%. Do you remember the other one we did the other night? I just got to show you this one, because I'm going to ask you how you feel about making predictions on this one. So I did another one, and this is my go-to guy here, the manatees. That was nice looking, right? If I had a thick magic marker, I could just put the line through all the points at one time. And so remember, if I go to regression, fitted line plot, and here I wanted what? The number of kills of manatees and the number of votes registered was the predictor. How do you feel now? 90.8% of the number of manatees, of the variation in the number of manatees killed is explained by the linear relationship with the number of votes registered. How do you feel about making predictions now? Folks, this is real world data. We ain't going to do much better than that unless you let me make the data up. Right? And 56% in the big scheme of things is not all that bad when you're looking at real life data either. When I start getting less than 50%, I start scratching my head going, am I really going to waste my time here and do this? I mean, I can do it for you, but is it worth anything? Right? 90%? Definitely. Right? So again, 90.8% of the variation in the number of manatees killed is explained by the linear relationship with the number of votes registered. That's very, very good. How do I know that? Because only 9.2% of the variation is coming from the scatter of the points about the line. And you can see, you don't have to look at me, you can see that, right? The points are really tight to that line, way tighter than the maximum. Let me ask you this. Can we figure out the correlation based off what I've given you here? You're going to take the square root of 0.908. You're going to get a plus or minus, or you're going to take the plus or the minus? Plus, positive slope, positive association. Okay. Now, I can sit here and we can do another problem and another problem and another problem, but you got what we got here, right? And I think about this. I gave you the statement right out of the book, that 90.8% of the variation in the number of manatees. That's right out of the textbook. But what is it really telling me? It's telling me how successful I am at fitting the line. The closer it is to 100%, the more successful it is, and the better I feel about making predictions. Or the better somebody should feel about making predictions. In other words, if you were going to do this work for somebody in another class, and you had like 2 quantitative variables, and you were looking at the relationship, you'd give them all this. You'd give them the scatter plot, the regression line on there, the regression line. You definitely want to give them R-squared. Because why do they want the data? Somebody wants them to make a prediction. You want to know if you can trust them or not. Okay? All right. So then we need to have a talk about what's left over here. In other words, I keep calling it the scatter the points about the line. So there's something called residuals. And I'm going to give it to you like this. It's the vertical distance from a point on your scatter plot to the line. Now, on Tuesday, if you wrote everything I write down, I called that an error. Yeah, I think I called it an error, right? I gave you that little line and said, look, there's all those errors. It's a residual. It's the vertical distance from a point to a line. It's the, how about if I call it the reason I'm calling it leftover, R-squared is telling you the part we're really interested in, and this is what's left over, right? This is telling me about the scatter of the points about the line. Okay, so there is a residual for every individual in your data set. And the way the residual is calculated is as follows. It's always the observed Y minus the predicted Y. In other words, it's always a Y minus a Y hat. This is from the data. This is from your line. It always needs to be in that order. If you flip-flop them, you're going to be off by a minus sign here. So in other words, back here, what we're looking at is this distance here. I'm going to pick that guy right there. That's the residual, right? That's the vertical distance. And you always take the observed, what's in the data, minus what the line would predict. So here's my question. You see that guy right there, that little dot there that's above the line? Would that have a positive residual or a negative residual? Is the Y observed bigger than the predicted? In other words, any point that is above the line will have a positive residual. Any point that is below the line will have a negative residual. Why? Because think about how it is. It's Y minus Y hat. If it's above the line, the Y is bigger than the predicted Y hat. If it's below the line, the Y is smaller than the predicted Y hat. How do I get a zero residual? If I've got a point and the line passes exactly through it, that will give me a zero residual. What does that mean? The predicted and the observed are exactly the same value. Okay? Now, what I kind of like to do here with this is let's pick one of these. right? We'll use what we got here, right? So I'm going to get rid of all this, and I'm going to come down here, and we'll pick a year, right? So we got to pick a year. So it doesn't make any difference. We can pick any year from 1977 through whatever it is, because there's a residual for every one of those years, right? Every one of the individuals, every one of the data points. So let's say we pick, just for the sake of things, let's say we pick 1979, all right? So I'm going to come over here, and I've got 1979. That's my individual. And then what do I have here? For 1979, I've got 481 boats registered. I don't know if you remember. It's not 481. It's actually 481,000. Remember they chopped off the 3 zeros at the end? And then what's the number of manatees killed in that year? The number of manatees killed is 24. Now, can I do this to you? That's your X, right? That's your Y. Yes? So if I'm going to calculate the residual, not only do I need to know the X and the Y for that particular individual, but I also need to know, what do I got to find here? I got to find Y hat, right? So I need your regression line. So I need this guy here that says, what is it? Kills is equal to minus 42.75. Excuse me, 45.27. Dude. Let's look at that again. 45.27. And then my slope is 0.1331. Right, so that looks just like any of the other lines, right? Hey, can we interpret the slope here while we're here? Just a little more practice. Right? So what does this tell me? I'm not going to write it out, but for each additional boat registered, the number of manatees killed increases by 0.1331, right? Okay? So how do I find Y hat here? I mean, I know I've got my actual terms in there, but Y hat here is going to be this, right? So I'm going to change that to Y minus 45.27 plus 0.1331. Does everybody understand why I'm plugging in 481, right? Because for the year 1979, 481 is the number of boats registered. So I need to figure out what my line predicts the number of manatees killed should be. So somebody going to need us a calculator here. This 0.4 minus 45.27 plus 0.1331 times 481. What was it? 18.75. So in other words, if somebody asked me to make a prediction for 481 boats registered, I would predict 18.75 manatees killed, right? So we really want the residual. And remember, it's always observed minus predicted. I said the words, but I wrote Y minus Y hat because Y is the observed, Y hat is the predicted. And here we know the observed was 24. Your residual here is a 5.25. And so what it's telling me is that point that represents 1979 is 5.25 points above the line, right? That's it. You okay with that? Could I have done any year? Nothing was special about 1979, right? I could have picked any individual. So what would have changed if I would have changed the year on you? Obviously, X would have changed, Y would have changed. I'd have had the same regression line. I'd have had a different Y hat, right? That's the reason I scroll back up. Because when somebody asks you to calculate the residual, you need the X and the Y, and you've got to have the line so that you can calculate Y hat. So there's a residual for every individual in your data set's my point here. Okay? Now, here's the thing. There's a little graph that goes along with these residuals. And again, it's another scatter plot, but there's something called a residual plot. And what we do is we plot the residuals versus your explanatory variable. So in other words, that's your y, that's your x. So it's a scatter plot, but we change what we put on the y. We put the residuals on the y instead of the response rate. Okay, so I want to show you how to get one of those. If I come over here and I get rid of this guy, I'm going to go back exactly where I was, stat, regression, fitted line plot. The only difference is everybody see these three buttons here at the bottom? There's like graphs and all this. I want to go to graphs. I want to go to graphs, and I want a residual plot, okay? But I want to come down here, and I need to click in that box because it's the residuals versus what variable. And for us, it's always the residuals versus the explanatory variable. And the explanatory variable is the number of votes registered, right? So it's going to give me a scatter plot. Oh, it's going to give me all kinds of stuff. There's your residual plot. And it gave me all the stuff I had before because we were doing that too, right? What I want you to notice is this. You see that dotted line? That's the zero residual, right? Those are the ones, if anybody had a zero residual, they were right on the line. What is that actually in terms of the original scatter plot? That's the regression line. That's what that's representing. Right? The zero residual is representing the regression line, the least squares regression line back in your original scatter plot. Okay? So you'll notice there's a point on here for every individual in the data set because every individual's got a particular residual. And see, this is the kind of thing we're looking for here. You see how nice this is? See how when you look and as you go across the different values of the explanatory variable, the points are just kind of following? In other words, it's kind of like a nice thing, right? They're all within here and, they're kind of got this nice even spread. See, this is supposed to confirm, how do you feel about making predictions here? Good, right? Because they're all kind of close. Looks like the line fits the data well. And you're going, dude, do I really need this for that? And the answer is, nah, I got to give you some thought about this, all right? I already knew stuff was good. Right? Did the residual plot confirm that? Yeah, I got that nice scatter, right? And so then you're supposed to ask me, well, if I get a good R squared, why would I be concerned about the residual plot? And you wouldn't be. If the R squared's good, close to 100% or something like that, you know what you're going to see here. You're going to see something that looks just like this nice spread of the points, right? So then the question is why would I care about the residual plot at all? Well, the reason I would care about the residual plot is, let's say your R squared's bad. Let's say it's less than 50%. Let's say it's like 40%. So we don't feel really good about making predictions. And so the reason I would look at my residual plot is because I would hope to see something like this. There's your zero residual. And so when I look at the residual plot, I would hope that I would see something that maybe looked like that's the reason is if my R squared is low, like 40, 30%, I would want to look at the residual plot to see if I can salvage anything. Because here's my question. You see from here to here, does the line fit the data really well for those values of the explanatory variable? And the answer is yes. How do you feel about making a prediction in that range? Good, right? Yep. Good fit. accurate predictions. How do you feel about out here? In the blue. Not a good fit. How do you feel about making predictions? I don't feel good. Right? So, look, if you ever take any higher level statistics courses, they're going to come back and talk to you about these residual plots again. For me to talk to you about them, if my R squared is good, I know exactly what we're going to see in the residual plot. Things are going to look good there too, right? You're going to see that nice even scatter about the zero residual. If it's bad, low, 40%, 30%, can I salvage anything? And this is the kind of thing I'm looking for. Is there any range of values here that the line actually fits the data well? If it is, I feel good there. Outside of there, I didn't feel good, right? You understand, I can still have something that looks like this in the residual plot and my R squared be bad, right? It can fit good for some range, and for the rest of it, it may not fit worth anything, right? So that's what we're looking for. That's all I got for you, in 1530 about why do I want to look at it. If my R squared's good shit, I know R squared's bad, then I'm looking for something like this. Okay? Here's my thought. Okay? And we've been through chapters 4, almost all the way through chapter 5, and I never did say anything to you about outliers. I mentioned it, but I never started plucking any out of the scatter plot or anything, right? So we want to look at this term. And the term is influential observations. Now, I'm going to point you to where I'm at in your text, because I don't want to have to write up everything that's in this little box here that's on page 143. An influential observation is an outlier. Now, outliers come in different flavors here. It says an observation is influential. In other words, it's got some influence over something. For a statistical calculation, if removing it would markedly change the result of the calculation. Now look, I'm going to write this for you. The two calculations me and you have here are look, I'm just going to write regression line because I told you anytime me and you's dealing with the regression line, it's the least squares. Those are my two calculations. So the only way to know if your observation is influential is you have to calculate both of these twice, with it and without it. You've got to take it out of the data to see if you see a big change here in your correlation and or your regression line. Does it move a bunch? Now, we're going to give you some heads up here. It says, the result of a statistical calculation may be of little practical use if it strongly depends on a few influential observations. In other words, I'm going to show you here in a second. If I can throw one in and make the correlation and the line look better, well, what the hell about the other 50? That's no good, right? That's what they mean. Now, more important than anything is what's the third little chunk here. It says points that are outliers in either the x or the y direction of the scatter plot are often influential for correlation. So here, it's x or y. So in other words, they're extreme in their x value or they're extreme in their y value, right? And then the other one is points that are outliers in the x direction are often influential for the least squares regression line. So down here, we're always worried here about the x, right? So in other words, their x value is extreme one way or the other, okay? Now, here's the way I would like to attack this with you. I got this little guy here. I just searched the internet for an applet for correlation and regression. Okay? And so what this is going to do is it's going to let me put points on a scatter plot. That little box, there's a scatter plot, right? And it's going to let me show you the least squares regression line as we do this. Now you notice I put 1 point on here. Are you expecting anything? Can I draw a line with 1 point? No. I need another. Yes? Are you shocked that the regression line went exactly through the 2 points? That's how many you need to draw a line. You see the correlation? 1. They would go exactly through there. So I keep filling in, right? You notice every time I click a little bit off the line, it moves a little bit, right? So what does it mean? I'm going to clear this and start over. So what does it mean to have, so I'm here, right? So what's it mean to be extreme in the x? Well, my x's here are on the low end, right? So extreme in the x would be on the high end. So what I want you to do is I want you to watch. If I come over here, and you see where my little cursor is, right? So I'm going to give you one that's extreme in the x. You see what the correlation is? You see where the line is? Folks, that would be what's called an influential observation. How do I know that? The correlation went from point 8 to point 1. The line went from being like this to like this. That's extreme in the x. I don't know how, I could stand here all day and I could have drew pictures all over the place there. I put one click on there, that's what you get. What happens if I drag that guy off? Nope. Now, I'm in such a habit of drawing things that are linear with the pen. Even when I'm clicking dots on the scatter plot, I'm really good at making a linear. So what's it mean to be extreme in the y? Correlation change a bunch? Hell, it went from positive to negative. Yep. I'm pretty sure I think with what I just showed you, I kind of explained to you what we're talking about with an influential observation, right? Now, you notice I made everything look worse there, right? And what I mean by that is I made the line move a bunch. I made the correlation get worse. Can I make it get better? See the correlation? I didn't have much of a correlation to start with, but I put that point right next to the line, the correlation got better. So here's my thing is when it says it markedly changed it, it doesn't always mean it gets worse. You can actually make things look better with an appropriate placed individual in your data set, right? In other words, I could have had correlation is negative 0.2. I can always set the line on there. If somebody would just come along and give me, I doubled the correlation. So I can make it look better than it really is, right? That's not good either. Okay? You understand? So all the ones I showed you to start with was I was making it look worse. But influential can make it look better than it is. And what I mean by better, the correlation's higher, the line fits the data better. And obviously, if the correlation's higher, we look at R squared, the line's going to fit the data better. Yes? Now, one warning here about all of this. You see this right here, and I'm going to put you a little arrow. So these ones that are extreme in the x, and they are influential on the regression line. Remember, it pulled the line towards them. Points. No, I shouldn't say points. That's like a math guide. Everything actually has a interpretation here. Observations that are extreme in the x will have a small see, my problem is you can't pick out influential observations for the least squares regression line by looking at the residual. Because what happens is when they're extreme in the x and they're influential for the regression line, they pull the line towards them, right? So naturally they're making their residual small. So you won't see them in a residual plot. That's the reason I'm writing it, right? So okay, if you're influential or you're extreme in the x, and that means you're going to be influential for the regression line, don't be looking for a large residual. It pulled the line towards it. It actually made itself have a small residual, even though it's extreme. Okay? All right. Here's what I'm thinking. what I've got left here in this chapter are some cautions and some things we need to be aware of, because you got to understand, as long as I got two quantitative variables, is anybody stopping me from calculating the correlation? Is anything ever stopping me from doing the regression line, scatter plot, and fitting the line? No. We're not doing any by hand. There's nothing stopping the software. You give me two quantitative variables, we'll calculate correlation, and we'll do all that work we did in those other problems, right? Are there still cautions that need to be had here that we need to pay attention to? And the answer is yes. So on Tuesday, we're going to come back, and I'm going to talk to with you about cautions. What I would like out of you, since there's not going to be any homework assignment this weekend, remember you're having a test on Thursday, so I kind of hope you'd start thinking about that, right? Is cautions. I would like for you to read, and then I'm going to mention what I want to mention. You know, I don't normally give you any readings. 146 to 150. There's some terms you want to be aware of. There's something called extrapolation. There's something called lurking variables. Those are going to be my biggies on Tuesday at the beginning of class. And there's something about association does not mean causation, does not imply cause and effect. Take a look at that so that I can just mention it like 10 minutes, and then we can move on to Chapter 6 on Tuesday, and then we'll talk a bit more about the test. All right? Debbie's got the ones for you guys there to give back. Rob's got your guys' here. The streamers, you're going to get yours back, but it's going to be much later tonight because I got some stuff I need to do when we get done here. Are we okay with this? Everybody follow, right? So no homework. Start looking at your material for the test, all right? And be careful going to the house, and we will see you on Tuesday.